Okay, so in this video, we're going to talk about enthalpy change, and I'm going to cover an energy level diagram. Now, so basically, over the last couple of years, for O-level exams, right, you have a mixture of energy profile diagrams and energy level diagrams coming out. So I think back in 2019, you have your energy profile diagram. 2020, it was an energy level diagram. 2021, it didn't really appear. 2022 was an energy profile diagram again. So what I'm going to do right now is I'm going to just cover a different type of energy level diagram. It's not a sketching, all right? So here they give you a diagram and you're expected to answer the question. All right, okay? So what I'm going to do first is I'm going to run through the question with you. So here you're shown, right, that in Haber process, ammonia is formed and you're given conditions and you're given the balanced chemical equation here. All right, okay? So I'm highlighting that in yellow. And then here you're given a table of bond energies, all right? So you have a single bond for nitrogen, your triple bond, your single NH bond, and your HH bond, all right, okay? Now it says here that formation of ammonia can be represented by this diagram shown below, all right? And so here you have your reactants. Now what's happening, if you look very carefully, all right, let me just circle that in red, your N2 becomes 2N, which means what? From your enthalpy change 1 is when you are breaking the triple bond. So your N triple bond breaks and you're going to get 2 single N atoms. Okay? And if you look at from stage 2 to stage 3, all right, what happens? Once again, if you look very carefully, we have, I'm going to circle in blue now, 3H2 forming 6H, which means to say you have 3 hydrogen molecules breaking to form 6 hydrogen atoms. Or let me just do it this way, 3HH. So 3HH times 2 is 6. All right, and then your delta H3 is your bond forming, and then so basically your N and your 6 H's, perhaps I should just do this, they come together and then they form 2 moles of ammonia. So you have bond forming. Recall, bond forming is an exothermic process, energy is released. Okay, and the question goes on to say this. All right, using bond energies provided, calculate enthalpy change for delta H1, H2, and H3. So now here you have, enthalpy change 1. You have breaking of your nitrogen triple bond, and that is 945. So enthalpy change 1 is very simply 945 kilojoules per mole. Now, you must recall this is chemistry, this is not math. So just because it is positive doesn't mean you do not write the plus sign. Please have the plus sign there to show the energy is absorbed. All right, okay, watch out for that. Now, enthalpy change 2 is the energy needed to break your 3 hydrogen bonds. So hydrogen is 435, right? So 435 times 3 will give us something like, give me a sec, let me just pull out my calculator. 435 and 3 gives us 1305. All right, so you have 1305, once again, kilojoules. And therefore, enthalpy change 2 will be positive 1305 kilojoules. All right. Now what about enthalpy change 3? All right. So enthalpy change 3 is bond forming, right? We have 1, 2, 3, 4, 5, 6, 7, 8. We have the N's and the H atoms coming together to form 2 moles of ammonia. So here we have the formation of 1, 2, 3, 4, 5, 6 NH bonds. So 6 NH. And that is basically 6 multiplied by NH is 390. And you get something like, once again, give me a sec, 390 and 6, 2340 kilojoules. All right, okay. And so this is your enthalpy change 3. This is an exothermic process. It is negative 2340 kilojoules per mole. That is basically it. All right, that's per mole there. Sorry about that. Okay, so this is enthalpy change 1 and 2 and 3. All right, and it says here, hence calculate the overall enthalpy change. So we know that enthalpy change, overall, is basically your energy absorbed to break bonds, add to your energy released when bonds are formed. So you take a positive plus a negative number. Once again, it's enthalpy change 1 plus enthalpy change 2 plus enthalpy change 3, correct? So you just basically have 945, 1305, 945 plus 1305 minus away, because energy is released, 2340. And this will give us, so 945 and 1305 minus away 2340, negative 90 kilojoules per mole. All right, and that is your overall enthalpy change. Okay, so that's part 2. And lastly, part 3 is this: is it endo or exo? So this is a question where I say, you need to be able to recall the format. This is also in my Fight Your Way to Distinction guidebook, and the structure is there. All right, it's always energy absorbed to break bonds in N2 and 3H2 is, now if you're not too sure, let me show you, okay? So here we have going up, energy being absorbed. Here we have coming down, energy being released. So notice how the energy absorbed is much less than the energy being released. Alright, okay, so here we're just going to convert that into words. What we saw in the energy profile diagram, which I drew the middle line, we're going to convert into words. So energy absorbed to break bonds is less Alright, it's less than energy released to form bonds in 2NH3. Now, just a word of caution, do not write energy required. Wrong, alright? It's always energy absorbed and energy released, alright? Okay? And then talk about enthalpy change. Enthalpy change is negative, hence reaction is exothermic. And that will give you your 2 marks. Alright, so I hope you found this video useful, and I'll see you in the next one.